So this particular training session is part of our free training sessions that we do. We call them our programmer to programmer training. The idea behind these training sessions is we want to deliver to really just people all over the world the same kind of high quality, in-depth training that you would find in a standard corporate training type of environment. Instead of having to always go off and watch a video or read a blog post or even learn from things like GitHub Copilot, these sessions give us a chance to present to you in this live format some type of interesting topic to deepen your skill and knowledge in some technology that we're talking about, and then giving you the ability to ask questions back to us during the training session, so that we can answer those for you live. The training session is going to go for about an hour and a half. It just depends upon the number of questions we get and how long it takes for me to go through the different code demonstrations and such. If you have questions as we're going along, I would ask you to put those questions in the Q&A box of the webinar. If you just have random comments you'd like to make or whatever, you can put those in the chat box. But if you've got actual questions, if you could put those in the Q&A box, that'll be helpful for me to make sure that I answer everyone's questions. If for whatever reason somebody asks a question that we don't have time to answer, or I just don't know the answer to it off the top of my head, I'll be following up and answering that question in the Discord group that we have. So what I'm going to do here real quick before we continue on is I'm going to give you a link to our Discord group. I'll put that into the chat here. And the benefit here to the Discord group is that if you've got other questions about things, you're welcome to ask in there. We actually had a person who wanted to attend today's session, but they had some trouble with Eventbrite. They messaged me in the Discord group, and I was able to help them out and get them the link that they needed so they could attend the session today. So the Discord group is a great way to reach out to me directly if you've got questions on things, questions about events, technical issues for accessing our events. So there's our Discord link, and I would encourage you to sign up for it. We don't have a lot of activity on the group yet. It's something that we've recently started, but of course, as we add more and more people, we're looking forward to the future interactions and stuff that we're going to be able to have with all of you to help strengthen and deepen all of our skills in programming. Okay. We have another training session coming up at the end of next week on next Friday. We're going to be focusing in on concurrency. We'll talk a little bit about concurrency today in terms of crafting memory-safe applications, but we'll go into a little bit of a deeper dive with concurrency next week. We do have some additional training sessions that I have in the back of my mind that are being planned. It's just a matter of fitting it into my schedule. So while we only have one more actually on the calendar, we will have additional training events coming up, and I'll be communicating that to you through the various emails and other means that we have to let you know about those. Before we dive into the actual coding part of this, let me quickly just give a quick overview of what Rust is for anybody who happens to be joining the session today and is not familiar with Rust. And before I do that, I actually have a question here about the video recording. Yes, so the way the video recording will work is this weekend, I will process the recording. I will also issue you a badge for attending the session today live. So over the weekend, you will receive an email that has a link to the recording, also a link to the badge that you can then attach to your LinkedIn profile if you would like to. Okay. All right. So, yes, question here. I had a question about the Rust and Leptos training session. Unfortunately, because of a bunch of other commitments that I had last week, I ended up having to cancel that. It kind of broke my heart to cancel it, but we only had a couple of people signed up for it, and the things that were on my plate that I had to take care of, it was going to be too much for me. So I am very sorry for having to cancel that. I very much want to do a Rust Leptos session in the future. And in fact, what I'm going to do for that session is we're going to do that 1-day session, and we're going to do that for free. So instead of making it a paid session, it will be a free session. That's my way of saying, thank you for signing up and sorry for canceling it. I almost never cancel anything, but I had to in this particular case. But we're going to get that scheduled again. We'll make it a full day session, and I will send out the usual notification. So I appreciate you asking about that and having an interest to want to participate in it. And like I said, we'll make that a free event as well. Okay, so let's go ahead and jump into talking about what Rust is here real quick, and then we're going to go right to our code demonstrations. So first of all, Rust is a systems programming language. When you think about programming in Rust, you're usually thinking in terms of applications that you might use C or C++ for. But I'll be honest with you, I have actually found Rust to be quite useful, even for programs that I might otherwise code in Python. Once you start to understand the memory safety stuff we're going to talk about today, once that kind of sinks in, you will find that Rust is much more approachable than really you ever thought before. And the key, though, is understanding how it works. But once you understand that, even things that you might have chosen to do in Python before, a much higher level language, are not that bad to do in Rust. And the nice thing about Rust is, because of all the memory safety and type safety, you know your application is going to work once you start coding it. It all compiles up and everything else. In fact, one of the things that I've found, because of the memory safety in Rust, I enjoy writing Rust code more, even though it can be a little bit more frustrating when writing it. I know that when I write it and it compiles and it runs, I know that it's really going to work. I'm not going to run into any type of other weird issues that I might encounter in other programming languages. That doesn't mean that nothing ever goes wrong in Rust. It's still programming and I'm still a human. But Rust's memory safety mechanism just gives me that extra sense of confidence and calm about the code that I'm writing and ultimately running. Zero cost abstractions. A lot of the things that Rust does as part of the compilation process, the way that it handles generics and things like that, allows us to have these zero cost abstractions. If you are utilizing other languages, let's say like a Python, and you're using things like the protocol class and stuff to define your interfaces, none of that stuff is zero cost. All of that stuff costs CPU resources and memory to set all of that up. Whereas Rust is going to give you those abstractions at zero cost. And of course, you can use Rust for a whole wide range of applications, building web servers, operating systems, whatever, but you can use it also just to automate your daily tasks if you want to. And I actually find that it works really, really well for that. So with that said, let's go ahead and dive in and do some programming here with Rust. I'm going to escape from there. Now, what I'm going to do is I'm going to take this URL right here. I'm going to put this into the chat and drop that in. So I've now put that into the chat for you. This URL is going to have all of the code for our demonstrations that we're going to do today. If you would like to code along with me and you are logged into GitHub with your personal account, what I would recommend you do is fork the repository and then create a code space. Fork the repository and create a code space. So fork it to your own account, create the code space, and what that will allow you to do is, because you have forked it, you can commit your changes back to the forked repository. If you create a code space directly off of my repository here, you won't be able to commit any of your changes. So if you do the forking, then create the code space, then you can commit those changes back to the repo. I do have some instructions on how to do that here under the Getting Started section. So feel free to go ahead and do that now if you would like to code along with me. If you don't want to code along with me and just want to watch, that's perfectly fine too. Another option you also have is, of course, you could just clone the repo to your local machine and use Rust locally if you'd like. Okay, with all of that said, let me go ahead and go over to my code space that I have here that I'll be running all of the examples through. Before I dive into the specific examples, let me give you a quick little overview of our structure here for our project. So when you go back later and look at this, you can understand how things are organized. So essentially, I've got one repository with a projects folder, and I've got a listing of the 11 demos that we're going to do. In the top level cargo TOML file, you'll see I have a listing of all of those projects. By having this top level cargo TOML file, I can have a bunch of individual projects and make things like the Rust analyzer happy in terms of understanding the project structure and giving me the nice code completion and other things like that that make coding in Rust so much more enjoyable. Anyways, if you were to add another project here, that's totally fine, but you would want to come and add it to the list of members under this top level cargo TOML. Okay, so let's go ahead and let's dive here into our first project. The way that I've set all of this up is I've pre-coded everything, except that I've commented out the code. So as we go through the demonstration here, I will be commenting and I'll be uncommenting and commenting code and talking about it. I'll also be offering a few comments in the code along the way. All of the changes that I make as we go through this, I will commit them at the end. So you'll have the final version of what we talked about here throughout the webinar. Okay. So let's go ahead and get started here and learn some things about memory management or memory safe programming and working with Rust. So let's start here with this first example. You'll see I've got a function here called immutable variable. In the function, I have a variable called num, and I'm assigning the number 2 to it. You can see by default, it's just going to make it an I32 type, basically using the rule of first assignment to determine what the type of the variable is automatically. If you wanted to be more explicit and give it a different specific type, of course, you have the ability to do that, but we're just going to stick with the default type that it assigns to it. Now, the first thing you'll notice here is I create the variable using the let statement. And then here on line 4, I attempt to assign to the variable. In Rust, variables by default are immutable. So by default, you cannot mutate a variable that you create. So how would I modify this code if I wanted to be able to mutate that variable? Down here, I would mark the variable as mutable by putting the MUT keyword in front of it. This is actually pretty cool if you think about it. Languages like Python, every variable you create is mutable. Some languages like JavaScript allow you to do let versus const. Let is mutable, const is immutable. But Rust out of the box just says, here's how you declare a variable with let. So all variables are declared with let. And by default, it's immutable. You actually have to add something to the let statement to say that you can mutate this variable. Now, what's really interesting about this is you'll notice that if I go to assign to it here, the compiler is actually going to complain about this. Okay, so it's going to be able to catch this at the step of compiling your program. This idea of catching these types of memory issues at compilation is at the heart of memory safety in Rust. You're going to be able to catch your memory problems not at runtime, but you'll be able to catch them for the most part when you're building your application. So if we were to come into here and run this mutable variable function like that, we would see in the output that the number is now 4. Now, all right, so there's our mutable variable. Another feature in Rust that you need to be aware of when it comes to variables is that Rust supports what's called variable shadowing. In Rust, you can redeclare a variable inside of the same code block. So for example, here, I'm going to say let num equal to 2, print it out. Then I'll say let num equal to 4. This is creating a new variable, okay? It's not mutating the original variable. The original variable is basically going to be destroyed, and the new variable here is going to be created, and we're going to assign the number 4 to it. The reason I mention this is that if someone was looking at this code for the very first time and they had never seen this before, they might somehow get the impression that this was like mutating the original variable. But that is not the case. That is not the case. It is actually creating a new variable. So if I want to mutate the original, it's the mute keyword. If I wanted to redeclare the variable, I can use the let statement. Now, later on, when we get into things like moving and borrowing, this idea of using this let statement will come back to us. All right, so a little bit of the basics there. Let's go to our next example. So as you know, in Rust, we do not have classes like you would in Python or C# or JavaScript. Instead, that primary building block that we're working with is called a struct. We can also connect methods to our struct using an impl block here. You could, if you wanted to, you could kind of think of this as like a class if you were trying to relate to another language, right? This would be the name of the class. This would be the data members. And then these would be the various methods that would be accessible either on the class definition itself or on the instances that are created. Well, the reason I want to talk about structs here in terms of the code that we're going to be working with, and in fact, we're not going to look at counter quite yet. We're going to look at a vector first. Is I want to point out something to you that's a little bit different with Rust compared to other programming languages. If you don't mind here for a moment, I'm going to write just a very little bit of JavaScript code. In JavaScript, I can create a variable, let's say called person. And on person, I could have an age, name, age, and city. Most people who are new to JavaScript will look at person and say, oh, it's a const. I guess I can't mutate it. Then they'll come in and write person.name and type in Bob, and they'll be surprised that they can mutate the person object. After all, it's marked as const, right? Well, what they don't realize is that in JavaScript, it's only the variable that is immutable. The actual object that it points to can be changed. So this code would not work because person variable is immutable. But this code would work because the person object is mutable. See the difference there? You could see where people could get confused by that because they're looking at this thinking, well, that should be immutable, but it's not because the immutability is only the assignment of the variable, not the actual object on the heap that the variable points to. Well, here's the cool thing about Rust. Not only does Rust make a variable immutable, but the actual object out in memory that it's pointing to is also immutable. So for example, here, if I say let v equal to this vector, and I come to the vector and I try to push 4 on it, that would work perfectly fine in JavaScript because you could add things to the array. But in Rust, it's not going to let you do that because not only is the variable immutable, but the actual vector that it points to is also immutable. So if I wanted to be able to mutate that vector, I'd have to come into here and I'd have to put the mute keyword, and then I would be able to push onto it. I don't know of any other language that provides that level of control and access to memory. Okay. Raise your hand if you think that's pretty cool. Anybody think that's pretty cool that it does that level of memory control, like out from the variable out to the heap? That when I first learned that about Rust, that's when I realized I was working really with a very different language. This was going to be a different type of programming experience because of this level of memory control. So the first question I had then is, well, how is it doing that? I mean, if you try to think about how would you implement a programming language where you actually are controlling what somebody's trying to do to an object on the heap. I know a lot of times when I teach React classes, the props that come into React components are supposed to be immutable, but you can't enforce that in the JavaScript language because JavaScript doesn't provide any type of stack-based control access to the heap. And that's exactly what Rust does. So the reason I have this counter struct over here that I already briefly described is I wanted to show you how it's accomplishing this. So let's take a look here at our struct. So just like the original example for vector, I'm creating the struct without the mute keyword, okay? Notice when I call counter.increment and decrement, I have the red squiggles because I can't mutate it. Well, how does it know that that method is going to mutate it? And that's the key to the secret sauce here. Over here in my impl definition, you'll notice I've got 3 kinds of functions here. The first function I have is more like what you would think of kind of as a static function on a class definition. It doesn't receive an instance. In fact, I'm going to use it to create an instance. This new function that you see in the way that I'm using it here, this is a common Rust idiom for creating objects. Rust does not technically support constructors because it doesn't have classes, but commonly you'll see where people will create a method like new or maybe from that will be used to generate a new instance of whatever struct you're working with. So that's what the new is doing. But the red squiggles here are coming from the increment and the decrement. I want you to notice something here. For those of you who are Python developers, you know that when you have an instance method on a class, that first parameter on the method is the self object, which is the instance. Rust follows a similar convention. We have the self parameter as that first parameter of the instance method. But we mark that self parameter as mutable. And so what that means is that when you call this function, it knows that this function is going to mutate that data. If we don't mark this as mutable, let's just say we do that and we can't mutate it. I'll explain the ampersand in a second. If I don't do that, then this code won't work because I can't mutate the members of the struct. So in order to mutate these, I have to mark this as mutable. So essentially, it enforces the immutability from this stack frame through defining the immutability or mutability of the stack frame that will be created here when the increment function is called. And that's the secret sauce. So essentially, it controls access to the heap by controlling access to all the stack frames that will be created when you call those functions on that struct that you're creating. Okay. All right. So now I want to correct myself in one thing. This is actually not creating something on the heap. It's actually creating something on the stack. But whether you're accessing it on the stack or through the heap, it's this mechanism here that's controlling whether or not you can mutate throughout the call stack that you're going to create. So that's how it's able to enforce all of that. So if we come down to here and we take a look at this one, now if I mark this variable as mutable, now I can call increment and decrement on that variable. And so now if I wanted to run this code down here, I could run this here real quick. Now, before we continue on, I want to briefly talk about this right here, actually. So when I was going through my discussion a few moments ago, I mentioned the heap incorrectly, and I want to clarify that here real quick. If you do a lot of work in languages like Python, JavaScript, C#, Java, C++, all of those instances that you create are always being placed onto the heap at runtime. But that's actually not what that's not what's happening here in Rust. You can put things on the heap, and we'll talk about box and stuff like that a little bit later on in our presentation. But when you see this code right here, even though we are used to things always being created on the heap in other languages, that's not what's happening here. This is actually creating an instance of counter on the stack. And the reason why it's being created on the stack is that we know the size, the memory size of this struct when we create it. So as you know, when you work with the stack, anything allocated on the stack gets automatically cleaned up when the function exits, right? But you can only put things on the stack when you know their size at compile time. If you don't know their size at compile time, you're forced to put it on the heap when the program actually runs. Unless we are intentionally using things like box to put things out onto the heap, our Rust stuff is always going to be creating things on the stack because we know that memory size here at compile time, and that's the key. So even though it might look like, if you were comparing it to other languages, that it was being put out on the heap, it actually is being put onto the stack. But we'll take a look at a heap example here in a few moments. Okay, so that was our second example. Let's take a look at our heap example here. So, as I just mentioned, when you create structs, they are generally allocated on the stack. When you go to put something on the heap, you're going to use one of these structs called a box. There's a couple of other ones that you can make use of as well, but we're talking about the box here at the moment. When I say box new, this is going to go out and dynamically allocate memory on the heap. And in this case, that memory that we allocate is going to hold the number 42. If I want to access not the box itself, but the data in the box, how do I go about doing that? Well, here I have two examples, and actually both of them give us the same result, which is actually a little bit confusing. So I'm going to run this real quick, and we'll take a look at the output, and you'll see I get 42 twice. When I was first learning Rust, and I used the box, and I was able to get this value twice, I was really confused. I wasn't sure, did I need to explicitly dereference the pointer to get to the 42 on the heap? Or did I just reference the box itself and it would just magically give me the value, right? What I learned later on was that when you are reading the data from the box, Rust will automatically dereference the box for you through coercion. Now, Rust doesn't do a tremendous amount of coercion. We don't really like a lot of automatic coercion going on in our programming, especially at a systems level. When we do things like JavaScript and Python, coercion happens, and most of us kind of view that with a little bit of a critical, confusing eye as to why did this work? In Rust, there's not a lot of coercion, but this is an example of one. If you reference this box, either by dereferencing it explicitly or just referencing the box directly, when you go to read from it, it will give you the data inside the box. That's cool. But what about if I want to modify that data? If you want to modify the data, you explicitly have to dereference the box. So if I try to do something like this, that's not going to work. I won't be able to take the number 84 and automatically update this data on the heap. Instead, I'm going to have to explicitly dereference it in order to access the contents of the box and modify the data. So while this automatic dereferencing happens as part of reading the data, it does not happen for modifying the data. Now let's go back to our earlier discussion that we had about being mutable versus immutable. Do the same rules apply here? Absolutely. So just like we saw earlier, mutability and immutability apply for simple values as well as structs and things like that on the stack. It's also going to apply for things that are allocated to the heap as well. Okay. All right. So let's come down to our next example. Now, this is one of the most frustrating things that you will encounter as a new Rust programmer. Let me come down here and uncomment this. As a new Rust programmer, you might think to yourself, oh, I've been doing programming for a long time. I know how to create a list or a vector or an array of something. I know how to iterate over that and print it out, or use a debugging capability like you see here to print it out. No big deal. Let's see if we can create maybe a simple list of numbers and print out the list of numbers. So you might come in and you might create your vector. Maybe I'll write a little print function here that I'm going to call, and I'll pass my vector into it, and my code should work, right? So if I come down to here and I run this, you'll see I have success. Well, you might think to yourself, well, maybe I'll print that vector again. Would that be a cool thing to do? I have a red squiggle. What's the red squiggle for? I just printed the vector right here. Mouse over. Use of a moved value. And that's when we realize I have encountered a different way of looking at programming and memory management. Here's what happened. When we called print vector, this vector that we created here, the ownership passed from the move example function to the print vector function that we invoked. So print vector receives this vector and now owns it. That means that after I call this function, v is no longer available because that function has taken ownership, and now that v can be deallocated once the print vector function here is done executing. You see, what's happening here in Rust is that the compiler is looking at where you create variables, where you use them, and then where you stop using them. So like in a C program where you would write a bunch of code to allocate and deallocate manually, Rust is basically inserting all of those types of commands as appropriate in the outputted compiled code, but you don't have to write the code to do that. You just use things, you follow the various move and borrowing rules that Rust has, that the compiler follows, and it takes care of cleaning all that stuff up for you. Well, that's great, but if you're used to programming in pretty much every other language, it would be very confusing as to why you couldn't print this out again. And the reason you can't is this vector no longer exists because ownership was transferred to here. When this code finished executing, that vector was destroyed. So the question then becomes, how would I go about calling print twice if I wanted to? I need to switch the code from doing a move to doing a borrow. So here, how this is going to work is that we're going to bring in the ampersand, which indicates I'm passing a reference so that you can borrow it. You don't own it. You can borrow it and use it, and then I'm going to keep ownership of it. You actually saw something similar to this in the mutable struct code. Remember the counter example here? See the ampersands? This is basically telling these methods that they will borrow the instance while they're doing their thing, but the ownership is still owned outside of that method. References can be mutable and they can be immutable, okay? So this is an example of a mutable reference. So you can borrow it, change it, and give it back. But you can also have immutable references. You can borrow it, read from it, and give it back. And that's what you see happening over here. So now what we're going to do is we're going to create that vector. I've marked this as a reference. You must put the ampersand not only on the type declaration of the parameter, but you must also put the ampersand on the V, okay, in order to move ownership. What you're basically doing here is you're moving ownership of this, or we're borrowing, I take it back, we're borrowing ownership from this stack frame into the stack frame that's going to be created when this function runs. Up here, we were taking the vector created in this stack frame and moving it to the stack frame here. So really what you're doing with this borrowing and moving is you're just controlling which stack frame has access to it. Some stack frames will actually own it, and when that stack frame ends, it's destroyed. Other stack frames will borrow it, use it while they have access to it, but then when the function call is over and the stack frame is destroyed, that ownership is still held by another stack frame. So you can see it's all controlled by these stack frames as we're calling our functions and exiting the functions. Anyways, here, because I'm now letting print vector borrow the function or borrow the vector, if I go to run this code, I can now print it twice, okay? Now, can we do a mutable reference or a mutable borrow? Absolutely. We saw that with the counter already, but let's look at this code here. So here, all I have to do is introduce the ampersand mute into the variable declaration. I can iterate over the vector, modify the elements referenced by each position in the vector. And then down here, I can add 1 to each element and then print it. Notice that when I pass something in as a mutable reference, I have to include the mute as part of the parameter here. So you are reminded of that mutable reference, both in the function definition, but also in the calling of that function, right? That actually helps you write code that you're fully aware of how it's working. If you only put this on the declaration here of the parameter and you were trying to review this code, it would be unclear to you without looking at the function definition whether or not we were doing a mutable reference or just a reference or doing a borrow or doing a move without putting these qualifiers here. So to kind of summarize that, if you see code where you're just simply passing the variable into a function, that is generally going to be a move. If you see where we're passing it with an ampersand, that's going to be an immutable reference that we're borrowing, or that the function you're calling is borrowing. If you see the ampersand mute, that's a mutable reference that the function you're calling is borrowing. All right, so to summarize quickly before I move to the next demonstration, you're starting to get a real idea here that when you write your Rust code, you're really having to think about who owns the data. And the way that is all controlled is by who owns the variable, and that ownership is transferred between stack frames. So if you were coming from another programming language, let's say like Python, and let's say your knowledge of Python is from doing some things in data science in Jupyter Notebooks, and you wanted to jump over to Rust. When you jump over to Rust, if you're not familiar with things like call stacks and stack frames and things like that, you'd have to learn some more computer science type stuff on those topics before you could really get into Rust. So Python is really easy because you don't really have to know anything about the stack or the heap or stack frames or whatever. It just kind of works. In Rust, when you go a little bit deeper, you now have to start thinking about those things. The difference between Rust and, let's say, C or C++, in C or C++, you do have to know about stack frames and heaps, but you don't really care who owns the information. Sure, when you're writing a real program, you do follow certain patterns like RAII and stuff to manage how you create and destroy objects, but the actual language itself lets you do whatever you want. In terms of who owns what, who's changing what, you just write the code for whatever you want to do, and C and C++ aren't even paying attention to that. In Rust, it's paying attention to that. So you understand what can change the variables and stuff that you're working with. All right, let's take a look at an example here as it relates to iteration. Okay. So here, I've got a cart item over here like that. Let me uncomment my function call down here. I have a cart item over here. I have a vector of cart items. I'm going to come into here, and I'm going to iterate over the cart, and I want to set the quantity of each item to 0. What you will notice here is I'm using cart.iter. Now, if I just had cart.iter here, like this code will not work because this sets up an iterator. But as I iterate over the items, you'll notice it's not mutable. It's just a reference, an immutable reference that I'm borrowing. If I want to set up an iterator that gives me back a mutable reference, so I could actually modify the contents of the vector, then I call the iter_mute. And now that's going to give me a mutable reference. And now I can modify that. If you have the inlaid type hints enabled in your editor, you can actually see what these type hints are. That is especially useful, especially when you're learning Rust. Now, once you start doing a bunch of Rust programming, sometimes those type hints can be a little bit annoying. They do take up space on the screen. But when you're learning this and you want to be clear about what data type you're getting from these functions, this is really helpful, okay? Now, if you take a look here at cart iter, this is going to just give me a reference. So here, because I want to modify it, I want to get that mutable reference. And here, because I want to just print it, I get the immutable one. You might be asking yourself, well, Eric, why don't I just always get a mutable reference then? And then I can just do whatever I want with it. Rust has some rules surrounding that. In Rust, a variable can have many immutable references, or it can have exactly one mutable reference and no immutable references. So every variable in Rust can have either multiple immutable references or a single mutable reference with no other references at all. And the compiler enforces that. Okay, the compiler enforces that. So yes, I'm getting a mutable reference here, but I would not be able to get another mutable reference of that same variable. Okay. And down here, I'm getting immutable references, but if I hold any immutable references, I can't get a mutable reference. So these are the things that the Rust compiler is enforcing for us. Okay, so now let's come down into here. So now what I'm going to do is I'm going to iterate over these values here. But these values are not structs. Up here, when I iterated over the cart, I was iterating over a bunch of cart items, each of which was a struct. And I could simply just take the cart item.quantity and mutate the member. When you're working with things like numbers and you have a vector and you want to mutate them, you actually have to do a dereferencing in order to access that number in the vector and modify it. You do not have to dereference the struct, but you do have to dereference here the number. So I just wanted to highlight that here real quick in terms of working, let's say, with a vector of numbers and then modifying the contents of that vector. Okay, doing pretty good on time. Let's take a look at our next example here. In the previous iteration, we did borrowing of references each time we iterated. But sometimes we don't want to borrow the reference, we want to move the reference. For example, let's say I wanted to take this vector of products, and I wanted to update the quantity of each one to -5 and basically produce a I wanted to modify the quantity of each one by -5. Okay, so I'll have my products in stock equal to products. I'm going to iterate over it. I'm going to mutate this. I'm going to filter out the products that don't have anything remaining in stock. And then I'm going to collect all of this into a new vector here. So if I come down to here and I run this code, you'll see I get my vector listed here twice. So I have my original products vector, which has all the products, okay? And then I've got my my new vector down here that has the inventory lowered by 5, and then only includes the apples and the bananas. Now, why does this code work? It works because I created a clone of product and mutated the clone. So I have the original product inventory, but then for each product, I'm cloning it to put it into the new vector. Well, what if I didn't create a clone? Let's say I tried to actually update this existing product. Well, I'm going to run into a problem. This vector up here is using this product. I'm trying to create a new vector here. Both of these vectors are not going to be able to reference these products, okay? So I'm going to have a problem. It's going to say, cannot be built of an iterator of elements type this. The trait is not implemented. The trait is not implemented. And all of this is happening because I did not make that clone. What I could do is I could come into here, and instead of making this clone, I could actually take each of the products from the original vector, and I could move it into the new vector. So let's say I didn't need the original vector at all. I simply just wanted to decrement the inventory. Well, making a clone for each product to decrement the inventory and ending up with two vectors is not really what I'm looking for. What I'm looking for instead is to produce a new vector that's going to have those inventories reduced, and I no longer need the original vector. Well, I can do that by using into iter. Into iter, instead of passing a reference into our closure function here, it's actually going to move the product into the new iterable that we're creating here, the new vector. Anyways, I'm going to mark that as mute so I can then mutate the value here. But what happens is, because I'm now moving this into the new vector, I can no longer call products. Why? Because products is no longer available because I'm not cloning and I'm moving everything into this new vector. So in this case here, I'd have to comment out this code because products is no longer available to me here. So now if I were to run this, I just get the one vector that I have here. So this is an example of where we have to think about what iteration is really doing. When we iterate over something and take the elements of one collection and use them to build another collection, are we moving the element from the original collection to the next one? Are we going to be making changes to that element from the original collection to produce the new one? These are things we have to think about in Rust and make sure we understand which vectors own what, where we are changing things. And so we have these different functions available to us to simply just iterate and give us references, which we could then clone, or to actually move the product into the new vector, avoid the clone, but the original vector is no longer available to us. It gets a little bit tricky as you start working with it. There's a lot of little things that you have to constantly keep in the back of your mind as you're working with Rust. Once you get used to thinking this way, it gets a lot easier. Not only that, once you start thinking of this way, you will start looking at other programming languages in a very different light. You'll really start to think about who owns what, even in a Python or JavaScript program. If you apply some of these principles in ways that you write your code in those other languages, you'll actually write, better code. Okay. Let's talk here about references. So I already briefly mentioned this, but I'll go ahead and do a quick demo on it here. So basically, I'm going to have two references. Okay. Oh, for the code space, if you go under dev container and you go under dev container JSON, you can see the extensions that I have installed here and the other settings. And you could really just copy and paste this to a local VS Code environment if you wanted to. Also, the Docker file that I'm using that has all the Rust tools and stuff like that configured is available from here. You can pull that down from Docker Hub if you want. Okay, so back over to references. You can see here that basically I have X and Y are both references to this 42. If I were to run this code, you'll see I get back this. Now, let's say I set up something like this. See how I made X a mutable reference? Okay. And let's come down to X equal 56 so we can mutate it. Here, cannot assign to X because it is borrowed. X is assigned to here, but it is already borrowed. What is it being borrowed by? It's being borrowed by Y. If I were to take this line of code out, then everything's fine. But the moment that Y has an immutable reference to X, I can no longer modify X. This is what I meant before when I said, if you have any immutable references, you cannot have a mutable reference to a variable. So this way, we don't have one piece of code depending upon a variable, but another piece of code unexpectedly modifying it. Unexpectedly modifying it. So once again, another example of memory safety here in Rust. And you'll see here, the compiler is like super helpful, right? The compiler, the Rust analyzer tooling, it does a really great job communicating these errors to you as you're doing your coding and everything else. Okay. Now let's talk about this code here. So I have a function here called read config file. All read config file does is it reads a file and then returns the contents. Because reading a file can result in an error, I'm using the result return type. But the result return type that I'm using is the specialized one for IO errors. So I can either get back an OK with a string value, or I can get back an error object with whatever the error is. Down here, when I call this read config file, I use an if let statement. And if the result of this is the OK, it read the file, then I'll get the contents, and I'm going to use a library called srd to deserialize the YAML into an actual config object in Rust. However, if I get an error back, I'm just going to print error reading config file. Well, over here, I have a config file, so I'm going to go into projects 08, and I'm going to say cargo run, and we should see there's the config file. There's the config output. Now, what if I gave this a bad file name? So I'll just give it a file that doesn't exist. If I run this, you'll see now I get error reading config file. Okay. So I get back this error if it can't read the file. No big deal. Now, let's say I wanted to combine the reading of the config file and the deserialization together. So down here, I'm going to use this code, and I'm going to call the code that I have over here called from file, which reads the contents and deserializes. So before I had a function that reads and then some code that deserialized, and they were separate, and now I'm putting them together. What problem am I going to have? Here's the problem I'm going to have. The error object that can be returned from this function is different than the error that I can return from this piece of code here. Remember how I said before, with Rust, it's all about the stack and knowing the size of something? Part of the reason why it's so memory safe is that it knows the size of things at compile time, which works perfect for putting it on the stack. But here's our problem. If I combine these two operations together, now I can have two kinds of errors get returned. What does that mean? If I have two kinds of errors, they're going to be different sizes in memory. I can't compile that and use that in the stack. If I don't know the size of something at compile time, I'm going to have to put it out on the heap. So one of the principles you'll learn when you start working with Rust is you'll recognize, oh, I'm putting this on the stack, I'm putting this on the stack, I'm putting this on the stack. And then you'll come across some code and you'll look at it and you'll realize, well, wait a second. I don't know the size of the error that I'm going to get back because it's different depending upon the error. So if I don't know the size of something, then where can I store it? Well, I can't store it on the stack, but I can push it to the heap. So what am I going to do? I'm going to use the core result type, and I'm going to return back for the error type a box-dyn standard error. What does that mean? Essentially, I'm going to take the error trait. You could think of a trait as like an interface, okay? The error trait, and I'm basically saying that I'm going to be returning some type of data structure that implements that trait. I don't know which one, and those data structures will be of different sizes, but they will implement that error trait. Because it's going to be of different sizes, I can't use the stack when compiling out this function. I'm going to have to push that error out to the heap. So because I could have different sized types or unknown size types being returned, I'm going to have to use the box and then set this up so that it will determine the size of memory at runtime. That's where the dyn keyword's coming in. We're not going to know the size of this until runtime. Well, what's the good and bad of this approach? Well, the good is that I can have two different kinds of errors come out of the function. The bad, though, is that we're giving up a little bit of our compile time memory safety and moving it more to runtime. This will happen occasionally in Rust. Now, I have seen people talk about this pattern as being kind of an anti-pattern. And I've done some research on it, Rust documentation, stuff like that. And even though I've heard people complain about using the box-dyn error, I haven't seen anything from the Rust team that says it's a bad approach or the wrong approach. I use it in the code that I write. But the reason I mention that is I have heard from some people where taking this approach to working with your errors maybe isn't always recommended. If you want to check that out on your own time and do some research on it, I would encourage you to do so. But anyways, in order to accommodate these different types of errors, I need to use that box-dyn error. And then here, this is my code where I'm basically returning back a config struct. And so I give it the file path. If we were to run this, you'll see it'll give me back. Let me run it from the right folder. So now I get back the actual config object, and I was able to combine the file reading and the deserializing into one function. Okay. Let's talk briefly here about a closure. Closures are really important, especially if you're going to be doing a lot of Leptos programming. If there was one way to describe the Leptos course, it's basically tons and tons of working with closures. So let's talk a little bit about how closures are going to work here. So first of all, I have a function here called add2. It has a parameter y, and then we're going to add x plus y. You'll notice that x actually comes from out here. X is not part of the function definition. It's just referenced by the function here in our code. Now, what I'm going to do here is I'm going to call our closure function here. And let's see, I'm going to make that not mutable. Perfect. And let's go ahead and run this code and look at the result that we get. I'm going to actually change to the folder so we can just say cargo run without scrolling down. So if you take a look here, here's the result that we get. I have x equal to 2. I reference x in the closure, which is just a function. Z is 3. I pass z into this add to closure or function. I get the result, and then I print it out. Now, let's say I marked this as mutable and wanted to modify the value of x here. Is this going to work? So I'll come down here and I'll run this code. Actually, let's not run it quite yet. I'm going to assign the value here. If I go to run this, you'll see the code works. But then watch what I'm going to do. I'm going to uncomment that. Okay. And I'm going to say add to z. And then I'm going to print this like that. All right. So we'll do that there. And take a look. I have a red squiggle. If I try to run this, it's not going to let me run it. The problem that I'm going to have is that when I referenced x inside of this closure, this created a borrow reference. Well, what have we learned about borrow references? If I have a borrow reference, I can't mutate the variable, right? Well, what am I trying to do here? I'm trying to mutate the variable while I still have a borrow reference. Now, this code was fine when these two lines of code were commented out. Why? Because we don't ever use this function later on in the code. So after I call the function here, this function can be destroyed. But the moment that I came down here and used this function again, okay, and called it, I can no longer reference x in this way because it's going to continue to borrow the variable x, okay? So when we come down here and we actually try to print all of this out, it's not going to work. So question becomes, how could I modify this code so that I could then modify x later on in the program? And that's where we come to this example here. What I'm going to do is I'm going to tell Rust to basically move x into the closure. So what that means is instead of borrowing it, we're moving the value of x into the closure. And so then I can come down here because it's no longer being borrowed. Now I can modify that value of x. So let me come down and uncomment that. So now because I'm going to move x into the closure, all this code will run as before, and then I can modify x, and then I can run it again. But here's what's going to be different. When I move the value of x here into the closure, right? Okay. When I move the value of x, it actually captures that value of 2. So down here, when I say add to again, it doesn't add 3 to y and then output 6. It still adds the 2 that we captured up here. So while, yes, I modified x, and so I have x and z are both 3, the result of doing this is I'm adding 3 to the 2 that was captured here when we did the move. So if you want to basically create a closure, but it doesn't continue to have a reference back to that outside variable, you can use the move. And we use that all the time in Leptos. Okay, now let's examine this a little bit deeper. If I want to move that value, what does that really mean? If I say move x into here, what is that doing? Well, to do that, it's making a copy of x, right? That way I can modify the original, and the new function now has the copy that it now owns because it was moved. So what does that mean? Well, let's take a look here at this code. I've got this person struct that I've created here, and it's got first name, last name, okay? And we're going to create a clone of this, and we'll have person 2. Now, I've got this full name function, and it's going to print out the person 2 first name and last name, okay? In fact, let's do it like this. Just so we get a little bit of a baseline here real quick. I'm going to come into here, and I'm going to say cargo run. And you'll see I get full name John Doe. So there's that full name closure referencing person from the outside, prints out the value right down here. If I come into here and create a clone of person, I'm going to define this new full name function here, okay? This is going to reference person 2. If I come down here and reference this full name, actually, we'll just call that first. So now I've got my full name. If I run this code, you'll see that I get John Doe still because I cloned it and then set it up to use this new variable. And here I'm redefining my closure function. If I come into here and set person.firstname to Tim, and I run this code again, you'll see it still outputs John Doe, okay? Because we're using this person 2 cloned version. If I were to create this one here and do that, now I'm going to create full name 2, and I get Tim Doe. Okay, so I have the original one, I clone it, redefine full name, modify the original struct, so on and so forth. Now, what if I did this? What if I were to say move and move the first person in there? And then what if I came into here and we'll do full name 2 like this. And I'm going to get rid of the, well, let's see, we'll do the clone. Yeah, okay, yeah, perfect. Notice here, when I move person into here, and this is going to take ownership of this, person is no longer available for me here to reference and to be able to clone it. So our ability to move things into these closures can make things a little bit more tricky here in our Rust coding. We're down to our last couple of minutes here. Let me jump to our next example here real quick. I've got 2 more important ones I want to show you here real fast. This one here talks about the idea of lifetimes. Sometimes when we work with Rust is not able to understand all of the relationships between the different variables and things that we're creating, and we have to give it a little bit of help. For example, let's take person 1, or take our address and person, and then our person reporter. I'm going to open up the move here to the side. So here I have struct address and struct person, and then I have my implementation here for creating a new person and then outputting the full name and outputting this mailing label. I create my person, I create my reporter, and I say reporter1 dot report here, okay? And so if I run this code here, let me open my, actually I can just run it by clicking run. we'll see that we get back our mailing label here for the report. Now, when I passed person in here, it moved the ownership of person to the reporter. So the reporter owns it. As long as the reporter's around, that person is guaranteed to be available. Of course, the problem is if I come down to here and try to run this code, this is not going to work because we don't own person anymore. So if I were to run this, we should see that we get an error here because we no longer have access to person. So when I pass person in again over here, it doesn't have access to it because we moved up here. But what if I did this instead? What if instead of moving, what if instead I passed a reference? Well, if I come into here and I pass a reference, then I should be able to access person again. But our problem is that as part of our person reporter, it's not set up for a reference. So what I'm going to have to do is bring in my version of the code that actually is expecting a reference, but we're going to have a problem. So down here in my person reporter, I now expect a reference. But here's the issue. If I just set this up to just receive a reference, so let's say I get rid of all of these extra little decorations. If I just pass a reference here into this reporter, and I come down here, and let's get rid of this reporter one here, okay? And let me add this code in here. I'm now going to have a problem. And let me, there we go. Okay. So I'm going to create this person here, right? I'm going to pass a reference to person and call reporter1.report. Then down here, I'm going to create another person and pass a reference into reporter2. Let's see if this code will work. So if I come back up to the top here and click run, you'll see that it's going to complain. The reason it's going to complain is that it doesn't know if this person that I'm passing a reference to is going to continue to live long enough for as long as reporter.1 is available, right? Because I'm passing a reference, but this person reporter requires that reference in order to do the report. Well, down here, what do? I'm redefining person, which means that what this thing is holding on to, this reference, is not going to be valid anymore. I need a way to tell Rust the connection between this reference and this code so that it will hold on to that value for as long as reporter.1 report and all of that is accessible. To do that, we create what are called lifetimes. And essentially what's going to happen here is when we pass in this reference to person, we're basically connecting this reference that we're passing in to the reference out here, and it will tell basically Rust to keep that reference around in memory for as long as this code needs it. So it doesn't deallocate that from memory when I do this operation down here or after I exit this function. So sometimes we have to give Rust a little bit of help when it can't determine if something will still be available and tell it, oh, we need to keep this around while this other code can still execute so that it will be available when that code runs. Because of that, down here, I can still say reporter1.report. And if I run this code, you'll see that down here like this. I wanted to talk a little bit about concurrency and memory and how Rust protects us there. As you all know, when you do multi-threaded programming, one of the biggest problems is managing shared state between the threads and protecting against those threads corrupting that state by accessing it or modifying it at the wrong times. Rust, through its memory safety mechanisms, helps to protect us against that. And let's take a quick look here at this example. Okay. And hold on 1 second. Okay. So let's take a quick look here at our code. We're using the request API here to call out to GitHub. We're just calling the regular public endpoint. I'm not using the API. To call out to GitHub to see if a particular user has an account. If they do, we'll return back an OK, Google user was found. If they're not found, we'll turn back an OK, GitHub user was not found. Down here in our code, we have a list of usernames that we're going to check here, okay? And then we're going to track the number of users that we're able to find in addition to the individual results. To set this up, we're going to use a mutex so that we control who accesses the data. And we're going to set this up with an ARC type, which is atomic reference counting. So I mentioned that there are other types that you can use to access dynamically allocated memory. One of those types is a reference counting mechanism, so that when you create the object and you have your reference and then other things reference it, the count goes up. If the count ever drops to 0, then it is deallocated. The atomic reference type is specifically designed so that we can do our multi-threaded coding and share that reference count object between the threads. If we were to use the standard reference count type and we tried to make use of that here and we modified our code to use that, the code will not compile because the regular reference counting type is not allowed to be used. So if I were to save this here, and let's see what this is complaining about. Right. RC mutex I32 cannot be sent between threads safely. So basically what it's doing is it's telling us that we can't use that particular kind of type to share data between the threads. So even before I try to run the code and get runtime errors and things aren't working out right, the Rust compiler is going to tell me that I can't use that particular type. Instead, I'm going to need to switch this back to the ARC. And we'll come back to here and make that ARC as well. Okay, so if we take a look here at the code, we're going to spawn a thread. In here, we're going to call fetch user. We're going to match our results here and then return back our fetch user result. And then down here, you can see where we iterate over, outputting each user, whether we found it or not. And then, of course, I've got the final count here. Let's run this code real quick. It should run for us. Give it a second to finish compiling here. By the way, for the dev container here, I'm not using the bare bones, like the minimum level dev container. I'm using the one above it because Rust is fairly intensive when it comes to compiling. So by using a little bit more powerful container here, we're able to compile things a little quicker. Anyways, you can see there's the code, and it updated that atomic reference count with the number of people that we were able to find. Okay, so there is our demonstration. I wish we had some more time together, but we don't. We're actually at the end of this now. It's been an hour and a half. I appreciate all of you hanging in here for the entire hour and a half. I hope you were able to learn some new things about working with Rust.